Welcome to CSC 201, Lesson 9.3, Counting Elements of Disjoint Sets, the addition rule. The addition rule says that if you have a finite set A, and you can break it into k distinct mutually disjoint subsets, A1, A2, up to AK. So that means different, distinct means different, so k different sets, and they have to be mutually disjoint, which means none of them have any elements in common. None of them have any elements in common. Then the number of elements in A is just the number of elements in A1 plus the number of elements in A2 plus the number of elements in AK. So an example of this would be how many three-digit numbers from 100 to 999, those are all the three-digit numbers if we include the 100 and 999, how many are divisible by 5? Okay, so we can identify numbers divisible by 5 pretty quickly by looking for numbers that end in 0 or 5. So another way of asking this is how many three-digit integers end in 0 or 5? So when I think about the set of numbers that end in 0, the set of three-digit integers that end in 0, and the set of three-digit integers that end in 5, they are most definitely disjoint, right? They don't have any elements in common, which means I can use this addition rule. So the number of three-digit integers that are divisible by 5 is going to equal the number of three-digit integers that end in 0 plus the number of three-digit integers that end in 5. So how do I figure out how many there are? Well, three-digit integers look like this, right? They have 3 digits. So the first digit, how many options are there for the first digit? Well, 1 through 9, right? 0 can't be the first digit because when there's a 0, we just don't write anything. So there are 9 options for the first digit. How many options for the second digit? 10, because we could have 0 through 9. And then for the third digit, if it has to end in 0, there's only one possible entry for the third digit. Okay, so that's 90 three-digit integers that end in 0. And then how many three-digit integers end in 5? So I have 3 digits. The first digit has 9 possibilities. The second digit has 10. And the third digit has 1, right? Because it has to end in 5. So 5 is the only option, so there's only one option. So then we do 90 plus 90, and we get 180. Okay, the difference rule says that if A is a finite set and B is a subset of A, then the number of elements in A minus B, which you might recall A minus B is A, but take all the elements in A, but then take away any elements that are in B. So a little Venn diagram. Here's A, here's B. So A minus B is everything in A, but minus the things that are also in B. So A minus B would just be all of this, minus that intersection part. And the way you calculate the number of elements in there is to just take the number of elements in A and subtract the number of elements in B. Okay, so let's do an example of this. A certain computer access password consists of 3 to 5 uppercase letters with repetitions allowed. How many different passwords are possible? So uppercase letters, there are 26 of those, 26 possibilities for each entry of your password. And you can have a 3-letter password or a 4-letter or a 5-letter. So for a 3-letter password, there would be 26 plus 26 plus 26 possible passwords, right? But you could also have a 4-letter password, and a 3-letter password and a 4-letter password have nothing in common. So those two sets would be disjoint, which means that I can use the addition property. So I'm going to add, this should have been times. So this is 26 times 26 times 26. Those are the possibilities for a 3-digit password. And then add how many possibilities there are for a 4-digit password, which is 26 times 26 times 26 times 26. And then add the number of possible 5-digit passwords, which is 26 times 26 times 26 times 26 times 26. And this comes out to, I've already done the arithmetic for you, 12,355,928 possible passwords. And that's allowing repetition, right? We are allowed to repeat a character. Now, how many different passwords have no repeated letter? So if I'm not going to repeat a letter, then, and I'm using a 3-digit passcode, then I would have 26 times 25 times 24, right? Because I have 26 for the first choice, but then when I choose the second letter in my password, I can't use the one I already used, so I only have 25 left. And when I choose the third letter of my password, I can't use either of the two I've already used, so I only have 24. And then that's how many 3-digit passwords have no repeats. And 4-digit passwords that have no repeats would be 26 plus 25 plus 24. Oops, that should be times. 26 times 25 times 24 times 23. And then for 5-digit passwords, 26 times 25 times 24 times 23 times 22. And that comes out to 8,268,000 passwords where no letter is repeated. So how many different passwords have at least one repeated letter? Okay, so these are all the passwords. Some of them are repeated, some of them are not, right? Some of them have a repeated character, some do not. This is just all the possible passwords. This is the passwords that have no repeats. So if you take the passwords that have no repeats away from all the passwords, you're left with passwords that have repeats, at least one repeat. Okay, so all I have to do is subtract 12,355,928 minus 8,268,000, and we get 4,087,928 passwords where at least one letter is repeated. So this last calculation here, this was an example of the difference rule. So I was doing all the passwords, take away the passwords that have no repeats, and you're left with at least one repeat. Now, if all passwords are equally likely, what's the probability that a randomly chosen password has at least one repeated letter? So the probability at least one repeated, right, we would calculate as the number of passwords with a repeat divided by the number of total passwords. Okay, and that would be, we already calculated in the last question how many passwords have at least one repeat, and that was the 4 million number, 4,087,928. The total number of passwords was 12 million. That can't be right. I must have copied that wrong. But it comes out to about 33%. Yeah, just checked. These two numbers were correct. Yep. So this is the number of passwords that have a repeat, and this is the number of total passwords, repeats and no repeats. About 30%, 33% of passwords will have a repeat. Okay, so the probability of the complement of an event. If S is a finite sample space and A is an event in S, then the probability of A complement, which remember A complement is just all the things that aren't in A, is 1 minus the probability of A. So like really basic example, like the probability that it will rain tomorrow is, I don't know, let's just make up a number, 30%. So the probability that it won't rain, which is the complement of rain, would be 70%. 1 minus 0.3 or 70%. Okay, so that's like the most basic example. When there's just two, the sample space is rain and no rain. So the probability of rain is 30%. The probability of no rain, the complement of rain, would be 70%. Let's see if we can use this concept on the previous question. I want to calculate, again, in a different way, the probability that a randomly chosen password has at least one repeated letter. So I could say the probability that we have at least one repeated. Well, the complement of having at least one repeated is having none repeated. So this would be 1 minus the probability that no letters are repeated. No repeats. Okay. So 1 minus the probability that there are no repeats would be the number of passwords that have no repeats in them, which was 8,268,000, divided by the total number of passwords, which was 12,355,928. So that is approximately 1 minus 0.67, which is 33%. Okay, so I got the same answer using the complement rule as I did calculating directly. All right, the inclusion-exclusion rule for 2 or 3 sets. If A, B, and C are any finite sets, then the number of elements in the union, the number of elements in A union B, you can just add the number of elements of A plus the number of elements of B, but you have to be careful not to add things twice, right? So if there's something in the intersection that when you count the number of elements in A, it gets counted, and then when you count the number of elements in B, it gets counted again. So we have to subtract out the things that we counted twice. So add the number of elements in A and the number of elements in B, and then subtract out the intersection. This is just a generalization of the addition rule we used earlier. We didn't have this part, right? This part was gone. And the only reason that worked is because we made the explicit requirement that this intersection be empty. We said A and B have to be disjoint, which means there's nothing in their intersection. You can still use a modification of this rule if there's something in their intersection by subtracting whatever's in there. And then similarly, we have a rule for 3 sets. If you want to add the number of elements in A union B union C, you want to figure out how many is in this whole thing, add up the elements in A, in B, and in C, but then carefully subtract the intersections, right? Subtract the intersection A and B, A and C, and B and C. And then these guys right in the middle here got added 3 times. So when we did each of these intersections, we subtracted them off once. And then we have to subtract them off again for the third time in this intersection of all three. So let's do an example. How many integers from 1 to 1,000 are multiples of 3 or multiples of 5? Multiples of 3 or multiples of 5 from 1 to 1,000. Okay, so how many multiples of 3 from 1 to 1,000? I'm going to write up here. Multiples of 3. Okay, well, the smallest one is 3. Between 1 and 1,000, the smallest one is 3. And that is 3 times 1. And then the next one would be 6, which is 3 times 2. And then 9, which is 3 times 3. And then the last one, the last multiple of 3 before you hit 1,000 is 999. And that is 3 times 333. So you can see that I'm by writing it as 3 times an integer, writing each of the multiples of 3 as 3 times an integer, I've actually set up a counter. I have 1, 2, 3, 4, blah, 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 until I hit 333. I have 333 multiples of 3. So 333 multiples of 3 between 1 and 1,000. Okay, how many multiples of 5 do I have? So multiples of 5, I have 5, which is 5 times 1. That's the first multiple of 5 between 1 and 1,000. The next one is 10. That's 5 times 2. And then 15, which is 5 times 3. And then I keep going, and let's see, the last one, this takes a little bit of, so 1,000 actually is a multiple of 5. So the last one is 1,000, and it is 5 times 200. So it looks like I have 200 multiples of 5, because by writing each of them as 5 times an integer, I've created a counter that I can follow. I have 1, 2, 3, blah, 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 200 multiples of 5. Now, the problem is that I have counted some numbers twice. There are numbers that are both a multiple of 3 and a multiple of 5. Like 15 is in this list because 15 is 3 times 5. And 15 is in this list because it's 5 times 3. So numbers that are multiples of both 5 and 3 are multiples of 15. So here's my multiples of 5. That's here. And then multiples of 15. My first one is 15, and that's 15 times 1. Then 30, which is 15 times 2. And then I keep going. And then the last one, I sort of just started at 1,000, and I said, okay, 1,000 is not a multiple of 3. It's not a multiple of 15. And then I just sort of played on my calculator until I found one that was, I only have to check like the 15 numbers below, right? So I can just keep going down by 1 until I find one. So you could try 999. 999 divided by 15, not an integer. 998 divided by 15, not an integer. And you keep going down by 1, you're not going to have to go more than 15 steps, right? You're going to find a multiple of 15 if you go at least 15 steps. And so I found one that was 990. And that ends up being 15 times 66. So I have 66 multiples of 15. 1, 2, blah, 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 66. So the number of multiples of 3 or 5 would be add the multiples of 3, 333, to the multiples of 5, which is 200, but then subtract the numbers that are multiples of both. Those are multiples of 15. So we subtract 66, and we get 467 numbers that are multiples of 3 or 5. And just to clarify, I am counting multiples of 15. I just don't want to count them twice, right? I counted them with the multiples of 3, like 15 and 30 and 45 and 60. Those are all multiples of 3. So they got counted as part of this 333. And then when I did the multiples of 5, I counted 15 again, and 30 and 45. Those are all multiples of 5. So I counted them again. They're also part of this 200. So there's some numbers that I counted once in the multiples of 3 and again in the multiples of 5. So I want to subtract them so that they only get counted once. So I subtract them out so that they only get counted once. How many integers from 1 to 1,000 are neither multiples of 3 nor multiples of 15? Well, there are 1,000 integers between 1 and 1,000. 467 of them are multiples of 3 or 5. So take away those ones that are a multiple of 3 or a multiple of 5, and what you're left with is 533 integers that are neither a multiple of 3 nor a multiple of 5. Okay, last example. A professor in a discrete math class surveys her students to find out what classes they have already taken and finds that of the 50 students in her class, we have a bunch of numbers here. 30 took pre-calc, 18 took calc, and 26 took Python. Now, these are numbers like 30 students checked off that they took pre-calculus. That doesn't mean they only took pre-calculus. Okay, they could have taken pre-calculus and other things. Same with calculus and Python. Now, 9 took both pre-calculus and calculus. 9 checked off both of these things, but also potentially Python. We just know 9 took both pre-calculus and calculus. 16 took pre-calculus and Python, and 8 took both calculus and Python. Now, these 8 who took both calculus and Python, it does not exclude students who took all 3. Okay, so some of these students may have taken all 3. We don't know yet. And 47 took at least one of the 3 courses. So at least one. How many students did not take any? So the complement of taking at least one course would be taking none, because at least one is 1 or 2 or 3. So the only other option is that you took none. So there were 50 students in the class. 47 took at least one, which means 3. There were only 3 left, and they took none. Okay, how many students took all 3 courses? So this, I'm going to use the rule from the previous page that if I want to calculate the union, which is not what I want to calculate, but it's just the rule that we learned, the number of elements in the union of students who took pre-calculus, calculus, and Python. I'll use Y for Python so I don't have 2 P's. Okay, that is the number of students who took pre-calculus plus the number who took calculus plus the number who took Python minus all the intersections, minus the number in pre-calc and calc, minus the number in pre-calc and Python, minus the number in calculus and Python, minus the number in all 3, pre-calculus and calculus and Python. Okay, so the purpose of this is that I know this number. This is 47. 47 students were in the union. 47 students took at least one of these. Okay, I know this number, I know this number, and I know this number. This was 30, 18, and 26. These 3 intersections were given. And so this is the only number that I don't know in this equation, and that's the number I'm looking for. How many students took all 3, pre-calculus and calculus and Python? So let's put all these numbers in. So I have 47 equals 30 plus 18 plus 26 minus 9 minus 16 minus 8 minus the number who were enrolled in all 3. And when I solve for the number in all 3, let's see, I get 47 equals 41 minus the number of students who took all three, which tells me the number who took all three would be 47 minus 41, which is 6. And then how many students took pre-calculus and calculus but not Python, and how many students took pre-calculus but neither calculus nor Python? Both of these questions can be answered most easily by drawing a Venn diagram. So I have pre-calculus, calculus, and Python. And then the universal set outside. Okay. So I know that 6, I just calculated in part B, 6 students took all three. There's 6 students in the intersection. And then the 3, and I'm going to work my way out. Now, this intersection, pre-calculus and calculus, is supposed to have 9 students in it. I've already put 6 of them in there. So there are 3 more who go in this region here. And then pre-calculus and Python, this intersection, is supposed to have 16 students in it. And I already have 6. So I need to put 10 in this last region. And then my calculus and Python intersection is supposed to have 8 students. I already accounted for 6 of them, so I'm going to put 2 more in the last region here. And then build my way out, work on the precalculus circle. Okay, so precalculus is supposed to have 30 students, and I've already accounted for 10, 16, 19 of them, so 11 more belong out here who only took precalculus and nothing else. And then calculus is supposed to have 18 students in it, and I've already accounted for 6, 8, 11, so there are 7 more. And then Python had 26 students, and I've already accounted for 18, so there are 8 more. And then we know that 3 students didn't take any of these courses, so I'll put 3 students out here. And now I can use this Venn diagram to answer the 2 questions. How many students took pre-calculus and calculus but not Python? So that is the intersection of pre-calculus and calculus, but not Python, so leave out the 6. So that is 3 students. And then how many students took pre-calculus but neither calculus nor Python? Pre-calculus but neither calculus nor Python. So that's the 11 who didn't take either of the other 2.